Okay. All right. So yeah, I agree. I think I could use some practice with permutations and combinations as well. Um, let's try something. Do you want to go through the question bank and IB and then just go through those problems?
Yeah, sure.
Let's do that, and then let's do a few of those permutation combination, and then we'll go through the um, Oxford book for some of the IB style problems that they have. 'Cause I'm sure, yeah, I
Okay.
know they have some of them at the end of the book. Okay, give me a second to pull them up. IB documents. My computer is really lagging today. Okay. I'm just gonna move over the, the textbook on this side just so I have a copy of it here. Um, we'll figure out what chapters it is in a bit. Okay. Uh, topic wise, fourth edition. Oh wait, no. I want the online one, not the. I think the trick with combinations and permutations, like the quiz we just took, kind of my approach isn't to kind of, I try and stray away from the formulas. I just try and think of it logically, just step by step, how to do it. Like, because I don't know of any other way to do it. Otherwise, it gets
I think
very
it's just so
complicated.
circumstantial.
Yeah,
Yeah, I think it's just so circumstantial that I just don't understand it. Like a lot of the time,
or
I feel like everything else with enough practice, you get a hang of it. But with this, it's like every question is so different.
yeah, and with enough practice you can kind of get a general idea there, and that's the thing. I don't think it's necessarily like a general rule you can always follow. It's something you'll like, it's more something you kind of have to just apply. Okay, we did this problem, right? This was in the problems from 2017. Have you gotten a chance to
Yeah,
do this
yeah,
yet?
we
Do
did.
you want to do this again, or do
I
you want
was
to
that
go?
was my next question. I just started it and then
Okay,
I joined your call. So I was literally
sure.
on A.
Do you want to do this one right now, or do you want to do another one?
We can do this one because I was about to do it
Sure.
anyway. So
Okay. All right. So there's 12 students, and they're set up in desks. Um, ironically, they're taking a test in advanced combinatorics. I would probably fail that test, but that's beside the point. The exam room is set out in 3 rows of 4 desks, okay? And the invigilator, so like a proctor, is at the front of the room. Okay. Two of the students, Helen and Nikki, are suspected of cheating. Bad Helen and Nikki. Find the number of ways that 12 students may be arranged. So for the first one, what would you do?
are there 12 desks?
Yeah, there's 12 desks.
Yeah. So then it's just 12 factorial, right?
Exactly. It's just 12 factorial. And that's just pure logic. That's just saying, okay, well, it doesn't matter whether I put them in like three rows of 4, or I just put them out in a straight line. It's still 12 factorial ways of arranging. Or you can think, okay, 12 options for the first desk, 11, 10, and so on and so forth. Okay, now find the number of ways the students may be arranged if Helen and Nikki must sit so that one is directly behind the other. Okay, so 1 and 5 is an option, 5 and 9 is an option, and so on and so forth. So how would you do this? Would you
So the
just
way
count
that I go
whatever?
about questions like this.
Mm-hmm.
Yeah, I actually draw it out. So I'll draw
Yeah.
out a big row and then I'll just write the number and then I'll multiply that. In this case, because it's 2 desks, I'll multiply it by 2.
Mm-hmm.
But if it was 3, then I'll multiply it by 6, right? And so because there's 3 ways to arrange it, so or six
Exactly.
ways to arrange it. So yeah, I would just find the amount and then I would do whatever's left over, the factorial of that.
Okay. Exactly. Perfect. So this is one arrangement. One, two, and then if you keep drawing those arrangements out, you'll get 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 arrangements of groups of them sitting together times. Um, well, there's 2 ways. Either Helen can be in the front or Helen can be in the back. So that's 2 ways. And then, like you said, the rest. That's 10. That would be 10 factorial, right? The rest. Yeah. I'm not going to go through the calculations because that's trivial. You can do that in a calculator. You can work that out. I think, once you're here, once you've figured out how the problem is set up, you're home free. Like, that's the main challenge here. That's the biggest hurdle, I would say, right? And I'm sure you would agree with that from your experience as well. Now, find the number of ways there can be arranged if they cannot sit next to each other in the same row. Okay, so they can't sit next to each other in the same row. Usually when it's can't, there's two ways. One is to say, okay, well, it could be 1 and 3, 1 and 4, or 2 and 4. I probably wouldn't do that. I would actually, it might be easier actually, but I would probably start with the 12 factorial and subtract the ones where they do sit next.
That's how I normally do the question.
Yeah, using the idea of a complement of a set, that really helps a lot of the time. So if they're not sitting next to each other, that's the complement of them are sitting next to each other. So it's 12 factorial minus the possibilities where they are sitting next to each other. Same idea as the previous problem, right? You kind of just count. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 possibilities of them sitting next to each other in the same row, times, same idea, two ways of them, either Helen on the left or Nikki on the left, times 10 factorial ways of arranging the rest, right? Okay, now let's check with the mark scheme, because we can check. 12 factorial, good. 16 times 10 factorial, exactly. And then part C is 12 factorial minus 9 times 2 times 10 factorial, exactly. Yeah, that's honestly the best way to approach these, just by kind of taking that step-by-step approach.
I think this one is kind of simple, but there was that one. Okay, there's a really bad like reverb for me. Do you hear that too?
Oh yeah, that's my audio settings on Zoom.
Okay.
I'll try and mute it. Yeah.
I mean, we can go. I eventually figured it out. It was a question on the quiz. Do you remember that one like that one question about like the tests being together, and like the three science tests that for some reason like tripped me so hard.
No, I completely understand that one. There's ways to do that using stuff we haven't learned, but it's that might actually make it even more complicated. So there's something called, like, instead of binomial, like multi-choose, there's something called multi-choosing. And that actually might help. And there's something called the stars and bars method. And that's something you would learn in a more advanced combinatorics class. But honestly, for that question, there's an easier way to do that, just once again by using logic. Do you have that problem?
Yeah, it was actually on the 2017 questions, I'm pretty sure.
I'll just write it out because I think I remember there were like 18 tests, right?
Yeah, it's here somewhere. Yeah, I remember literally doing it today, so it must be. And like I figured it out, every time, but it took really, really long.
Sure.
So yeah, it's in a trial examination session. A candidate at a school has 18 examination papers, including physics, chemistry, and biology. So no two of these papers can be taken consecutively. There's no restriction on the order of any other papers. Find the different number of orders in which these 18 examination papers may be taken.
Okay. My. Okay. So P, C, and B cannot be taken consecutively. Okay. That means I have a P. Okay. I'm going to say PCB is, I'm going to represent one of PCBs with a box, okay? So it's a box, and then I could have any one of the other 15 tests, another box. Oh, wait, that wouldn't work. Because you could fill more in here, right? That's the trick, okay. No two can be next to each other.
So I did where it was I solved for where it was 3 next to each other, which was pretty easy. But then when it was 2 next to each other, that's when it got really
okay. Got it. So let's take that approach where we start with the whole and subtract smaller. So we start with 18 factorial ways of arranging a total. Now let's take an exhaustive approach. So let's just say, obviously, 1 next to each other doesn't make any sense. So we can worry. Let's do 3 next to each other first, because that's the next easiest one to do, right? 3 consecutive exams. So you could have PCB, and then you as one group, and then you have 15 other choices, right? So if you have PCB as one group and then 15 other choices, sorry, let me know when you're ready. I don't want to like.
Yeah, my laptop was about to die, so I charged it.
Okay. So PCB, and then you have 15 other choices, right? So this would be 16 factorial times 3 factorial, because you have 3 ways of arranging the PCB and you have 16 factorial ways of arranging the other ones, right? So now 2 next to each other is where it gets tricky. I completely agree. So 2 next to each other would be P and C are next to each other. That's one possibility, but not B, right? P and C are next to each other, but not B. Okay. This is what I would do. P and C, and then one of the 15, I'm going to count that as a group. Okay? Another option is C and B, count that as a group with one of the other ones. And then the other option is P and B, count that as a group and then one of the other ones, right? Oh my, okay, this is tricky. And then you have how many more? You have 14 left here? Is that right or no? You still have 15 left here, right?
15 left, yeah.
Okay. 15. So now, here, how many choices do you have?
You have 15 choices of what it could be. Because wait, no. You have 16 left, so of the 16, one of them can't be it. So you have 15 choices of what you could put
Yes, there. Okay. So you have 15 choices for this spot, times, you could either do PC or CP, right? But then the problem is, if you move, what if, say that this was a bio here, and then what if you move this one over here? That would be problematic, wouldn't it?
Well, if you had 15 there, and then 16, and then 14, 13, 12, 11, 10, so you'd have 15 factorial and then times 16.
My concern is, here's the thing. We have PC and then 15, but then what if we put a bio here? When we count the ways to rearrange these, we're going to get a possibility where B is right next to P and C. And the problem is with that is then that goes to our 3 next combinations, not where it's just two next to each other. You know what I mean?
Yeah, I get what you mean. I think the way that when I looked over the problem, because I worked this out for so long, I think the way that yeah, so what I had first was 6, right? Because I'm just looking at how many ways that I could arrange the 3 to make 2 next to each other, so that's 6. And then I have 16, right? Which is I kind of grouped the 16 and 15 factorial. Oh, so you know how you have 15 and then 16? So I did 15 times 16 times 15 factorial, then again that times 15. And I
times 15 factorial. Here. Maybe we should start over with this part, the 2 next. The 3 next is solid, right? We have that down.
Mm-hmm.
It's the 2 next to each other that's bringing us problems. Okay, let's reimagine. Let's take another approach on this. Rather than trying to do it this way, let's just start with 1. Let's not even worry about all 3 cases. So 2 next to each other, we can have P and then C, and then any number of other tests and then a B, right? And then potentially other ones to the right of this. Does that seem right? We can have PC, and we could even have them over here. But at a minimum, we need to have 1 in the middle, right?
Mm-hmm. Yeah. So then that would be in itself a combination or a group of 4. So then you would figure out how to put those 4 next to each other, right? Or like, which is why I was like, why to put the times 15? That makes sense then, the times 15, because you have 15 places that you could put those.
But then the problem is, I could have another one in the middle, and that would still hold true to my principle of having just two next to each other.
I don't understand what you mean by that.
Sure. So right now it's PC, something else, and then a B.
Yeah.
If I just count the number of arrangements that's possible with this, I'm saying that I'm including all of the ones where two are next to each other, but then I'm leaving out the ones where PC are still next to each other, but instead of just one exam in between, there's two exams in between. I wouldn't be counting.
Oh, I see.
Okay, I remember I did an approach similar to this for that problem. Let me see, because it ended up working out pretty well. 18 factorial, 2 together. Okay. Let's see. I think I see. Or actually, maybe I don't, but we'll see. So we would need to have something here, something here, something here, something here, and then 14 other options. 14 other options here. Okay. So out of PCB, okay, maybe this is the way to do it. Out of P, C, and B, we have 3 choices here, right? Then out of P, C, and B, we have what did I do here? Okay, here's what I wrote, and I don't know what I did here. Maybe you can help me make sense of it. Then here we have 16 choices, then 15 choices, then 2 choices here, and then there's 14 factorial choices here, and then I drew arrows here, and I drew 15.
Yeah, that makes sense, because that's essentially what I did too. I just phrased it differently, because I had 3 times 2, which is the 6 in the front, which makes sense. Then I had times 16, which you also have. Then I had 15 factorial, but 15 times 14 factorial is just 15 factorial. So that's also what I had. And then I did an additional times 15, and the reason I did that was because those four spots could be situated 15 different ways.
15 different. I see. Okay. I understand this 15. I understand this 14 factorial. I'm a little bit confused about this though. What is going on here inside?
The inside? Well, I don't know why you have them in the middle, but I had the 2 right next to each other, which I just did like it's 6 different ways it could be arranged, right? Like, you know, the 2 next to each other. Because remember, we're trying to find the 2. They're not.
Okay. Yeah. So maybe the 2 should be here. You have 3 options here, 2 options here, and then you have it can't be bio. Okay, say that this is physics and say that this is chemistry. You have 16 options left, but it can't be bio, so you have to put a 15 here.
So it has to be 15 there.
And now you can do a bio, so you have how many left?
You have 16 options for the next one.
16?
Because you still have 16 books left, but you have 15 options for the one right after the 2. But then you have 16 options for the one after the 15, I think. Because if you only have 15, right? And then the bio comes back into play.
Yeah. The bio comes, okay, so we've chosen physics, we've chosen chemistry. So that's 2 books, you have 16 left. And we're putting a bio to the side. So we choose, so now out of 15, we're choosing 1 that leaves.
But this one, okay, you have 16 options left, right? And then you subtract 1 away from those 16 options, so you have 15 options left.
Yeah.
And then the next one, you have, then that would be,
That's why that's why I'm getting confused.
Oh yeah, that's so. I don't know. It made sense when I was doing it.
Yeah, no, it made sense when I was doing it too. I was able to actually get through this one pretty quick. See, and that's the other thing. Sometimes these problems just click, and sometimes they just work, and sometimes I have no idea what to do.
I know. That's my thing with them. It's like
Sure.
I can do as many practice problems as I want, but I'm not able to find like concrete patterns in anything.
Okay. Let's work through this one more time without any outside influence. So now that we have somewhat of a semblance of what to do, you start with you have three options for physics and chemistry and bio, and you have two options for chemistry and bio, and then okay, so 3 and 2. So now you've chosen out of the 18, you've chosen 2, so you have 16 left, right? So now out of those, I can pick any 16 here. Right? Any of those 16 I can pick here. Now, let's, now over here, I have to take bio out of play. So that means I have how many options left? 16.
15.
So that means I have 15 tests left, but I have to take.
No, because you took one for chem, one for bio. Then you took another one in that third spot. But that's 18 minus 3.
So you have 15 left here, right?
Mm-hmm.
And then once you've chosen 4 tests, you have 14 tests left. So that's 14 factorial ways of arranging that. And then you can put this group anywhere. You can put it 15 ways around it. So that's, yeah, okay. It could be here. Yeah. Okay. So it's 15.
Why did that make sense? When we did it earlier, it didn't make any sense.
Sometimes, yeah, that's the thing. Sometimes it doesn't work. Like you have to do it the right way, you know? It's weird. So that's 15 factorial because there's 15 times 14 ways, the factorial ways of arranging these things, times 3 times 2 times 16 times 15. I think that's right. And now if you do 18 factorial minus 16 factorial times 3 factorial minus all of this, you should get the right answer. My God. Okay. I think that's right. Let me confirm. Does that seem right to you?
Yeah, I'm pretty sure that's right.
Yeah, I think that's right. Okay. Well, yeah, you know, sometimes, and you know, honestly, if there's a problem like this that you get stuck on, I would just skip it and come back to it at the end, because some of these sometimes going through other problems helps because you approach things with a new light. Sometimes your mind just doesn't work like the way it has to work during a problem. So best just to come back to it. Yeah. Okay. Well.
That was fun.
I think this was one of the problems, right?
Yeah, that was one of the.
This one didn't seem too bad, actually.
Oh yeah. This one. No. I don't think we did we do this one before?
This was from 2013. No, we didn't do this one. We did a problem similar to this one. We did similar to this one.
Oh, it was 8 boys and 6 girls, or 2 girls, something like that.
But let's just do this real quick. These are not that bad. So without restrictions, how many? We have 6 factorial because there's 6 total. Number of ways this can be done if the 3 girls must sit together. Well, that's GGG is one group, and we have 3 boys left, right? That means this is 1, 2, 3, 4 factorial times 3 factorial, right? Done. Easy. Find the number of ways that this can be done if the 3 girls have to sit apart. Well, if they have to sit apart, that means they must all sit apart. Well, I could have girl, boy, girl, boy, girl, boy, or I could have boy, girl, boy, girl, boy, girl. To me, that's the only 2 ways that I can think of them all sitting apart, right? Is there any other way of making them all sit apart? Or no?
There
are actually.
No, I don't think so.
I think there are, because you could do girl, boy, boy, girl, boy, girl. Yeah.
Oh yeah, like on the inside.
But I would, yeah, for this one though, I would still write it all out. I wouldn't. I don't know how else I would do that. So, but I would write it out systematically. Mm-hmm.
Unfortunately, as hard as that other way was, that's the only way that I can like efficiently get these problems done. Mm-hmm. So I would do 1 minus 3 girls together, and then that minus 2 girls together.
You would do for this one?
Yeah.
You would do 6 factorial minus what?
6 factorial minus 3 factorial times 4 factorial minus, and then the way you would have 2 girls sit together, so that'd be.
Oh, okay. You want to do it that way? Okay, no, that's perfectly fine. You would do what? Go ahead.
I gotta draw it out. So you have 2 girls together, so girl, girl, and then so that's 3 options times 2 options, and then the third seat has to be a boy, so that gives you how many people are left? There's how many people total? That gives you how many options left?
You have 6 total. It's kind of it's essentially like the last problem. Then.
Yeah. So you have 6 left. So that means that there's 5 options for the one after, right? Mm-hmm. And then there's 6 options again.
Sorry. 6 minus 2 4s. So you have 4 options here, right?
4. Okay, there's one girl there, mm-hmm. Then another girl, then there has to be a boy there. So out of the
So I'll just do 3. I'll just say
3
because I've chosen a boy. So now I have 3. 2 boys left and 1 girl left, right?
So then that's 4.
And 2 then boys left and 1 girl left to choose from. So that's 3 then, right?
Yeah.
Not 4. And then 2 and then 1. Is that right or no?
So you took so one girl, so that's 2 girls gone, and then 1 boy, that's 3, and then you have 3 left. Yeah.
Mm-hmm. So 1 boy, so that means I have 2 boys left and 1 girl left. 3 ways to do it: put them here. 2 ways to put them here. One way to put them here. And then I have to multiply that by 1. Well, now I have to say, okay, well, I can put it here, here, or here. Right? You see what I'm saying? Yeah. So this would be 3 times 2 times 3 times 3 times 2 times 3. Okay. So it would be 6 factorial minus 3 factorial, 4 factorial, minus this business here. And let me just put that in the calculator and see if we get the right answer with the mark scheme, because I'm a little bit unsure about this, but I think our logic worked out. Minus 3 times 2 times 3 times 3 times 2 times 3. We get 252. Is that right? 144. Damn it. What did we do wrong?
It's definitely 6 factorial is the total. Mm-hmm. Minus 3 factorial, 4 factorial. That's definitely so that's definitely 3 girls. Or that's definitely like 3 girls sitting together. Mm-hmm. And 2 girls sitting together, so we have 6 spots total. And we have 2 girls sitting together, so that's 3 options times 2 options. Mm-hmm. Then for the third option, it has to be a boy, so that's 3 options. Mm-hmm. And then for the next one, it can be a girl or a boy. So you've taken 2 girls and 1 boy. That gives you 3 people left. So 3 times 2 times 1. Yeah, that makes
seems sense. Right.
Let me try it again and maybe
sure.
Just let me see. 6 factorial minus 4. I don't know how your computer works, but I have to keep going to number and then problem every time I have a
Wait. I think it's 144. If we change one of these to a 4, if we made this a 4, it would work. You get 144. And I noticed that last time as well. This one why is that a 4 and not a 3? I think that's where I'm getting stuck.
Oh, I think the way we have to do it is like skip over the one and then go like to the one after that and see how many possibilities there are for that one.
Okay, can you explain that one more time?
Like, I think what we have to do in these kind of problems is like you definitely have like the first two, right? And
Yeah.
like you know what those have to be. Then
Yeah.
there's one after that that you have to fill in a blank for. But I think the way that you would do these is you would skip over that one and then go to the one after. Because whenever we do it like going straight across, it's wrong.
It's wrong. Yeah. So you would have, okay, 3 and 2. That leaves you with 1 girl and 3 boys. That's 4 options here. And then you have to pick out of the 3 boys. That's 3 options here. So now you have 2 boys. Ah, interesting. That's weird. Why do we have to do that first? What's wrong with the other? I'm sure obviously the other approach is wrong. I'm not denying that. I definitely see that the other approach is wrong. I see that, but trying to figure out why. Why though? What's wrong with the other one? So if we started with, go ahead.
I was gonna say, if you think about it in terms of like, okay, so you have for the first two, you only have two that you can take, right? Like if you think about it as a permutation, you only have two things that you can arrange a certain number of ways.
Yeah.
That leaves four things, right? So that has to be in some way or another. You have to have four options for one of them. It's not possible that you don't.
Ah, I see. Okay, I see what you're saying. Because yeah, once you do the 3 and the 2, if we didn't take in that extra girl, we have to consider the fact that she could be here. Otherwise, if we just say, well, that's three boys, and that leaves us with, yeah.
Because if you count it out, right, you'd have one girl, and then three boys. It's only five people.
I see. You're not counting for everyone. Exactly. No. Okay. Perfect. That makes sense. Okay. Good. Can we do the other way real quick? I actually think we got all the other ways.
Yeah.
So if we did the other way, it would be girl, boy, girl, boy, girl, boy. That's one way. Boy, girl, boy, girl, boy, girl. Or girl, boy, girl, boy, girl. Or girl, boy, girl, boy, girl. There's no other ways you can separate the girls. So if you do it this way, then you have 3 options for the girls, 3 options for the boys, two options for the girl, 2 options for the boy, 1 girl, 1 boy. And then you essentially do that 3 times or 4 times, right? So 3 times 3 times 2 times 2 times 4. 3 times 3 times 2 times 2 times 4 gives me 144. Same answer. So do you see, like, sometimes this option is easier, sometimes the other method is easier. And now, obviously, if you're more comfortable doing it one way, and sometimes your mind only works one way. It's funny. Sometimes your mind only works one way, and you can't seem to understand why it works the other way. But you know, it's good to just do as many problems, and then on the test, like, not worry about it. You know, what's gonna happen is what's gonna happen. There's not much you can do about it. You know, just put your best foot forward, and then if it works out, great. If not, then, you know, once again, you'll be satisfied with yourself, because there's not much more you can do about it from your okay. Do you want to do any more of these, or do you want to go to the Oxford book?
We can do like one more, maybe.
This looks kind of tricky. This is from 2014. I think we might have done this one. Let's do another one that we haven't done.
Yeah, we've done.
Have we done this one? 7 toys, 3 children.
Yeah, we've done this one before. It was a while back, but I remember it.
What about this one? 6 people, circular table. Oh, no, there's no way. This is from 2009. There's no way we've done this one. Not at all. Okay. 6 people to sit at a circular table. 2 people cannot sit immediately beside. How many ways can they be seated? Okay. So if I have A, B, C, D, E, F, right? How many ways without restrictions, how many ways can they sit?
6. Was it 6 people, right? Then yeah, six factorial ways.
It's actually, so this is a rule. Whenever you have a circle, it's n minus 1 factorial. It would be 5 factorial. Reason being, yes, you could put them out in a straight line, but so then it would be 6 factorial, but you have to divide out the ways. Because in a circle, A, B, C, D, E is the same as B, C, D, E, A, and that's the same as C, D, E, A, because it's a circle, right? So it does, we're over counting. So we have to do 6 factorial divided by 6, and that'll give us 5 factorial. Oh, sorry. Actually, but yeah. So in a circle, that's just the rule. It's 5 factorial. It's n minus 1 factorial because you have that repetition. So you start with 5 factorial without restrictions, and now 2 of them are not to sit. So we subtract the ways that 2 of them do sit next to each other. Okay, so now we essentially do the same thing, except we treat A, B as a unit, right? So now what would it be? It would be 1, 2, 3, 4, 5. 5 factorial over 5 ways. So it's 4 factorial times 2 factorial. Does that seem right?
That makes sense to me.
Because it's essentially 1, 2, 3, 4, 5. 4 factorial ways of putting the groups in a circle, and then 2 factorial, you could have AB or BA. So whatever that answer is, let's check the mark scheme. 5 factorial minus 2 times 4 factorial. Exactly that. Yeah. Okay. Have you done this one yet? It's in 2017.
Yeah, I did that. I was looking for that one actually.
This one was kind of hard in my opinion. I mean.
Yeah, it seemed easy enough, and then it wasn't.
Yeah, it was just this part that seemed really hard. The mean, and once you realize it's just a binomial, right? Whenever it's a binomial distribution, you get very lucky because the formulas are very nice. But let's do this one because
the mean was actually easy for me. The mean and the variance.
Yeah, that's what I'm saying. Like because it's binomial, it's just NP and NP times 1 minus P. Easy.
Yeah.
This is the hard part. How do you show that the probability that Chloe wins is 3/8? Chloe wins if no matches occur, right? So if I have A, B, C, D, Chloe wins if either one match occurs. Sorry, Chloe does not win if either one match or 2 matches or 3 matches. 3 matches implies 4 matches, right? If you have 3 cards that match, the 4th one has to match. So I would do a systematic approach on this one. I would say, so it would be 1, the probability 1 minus the probability that she doesn't win. The way that she doesn't win, first of all, is if there's 1 match. How many ways are there of 1 match? Well, I could have A, C, D, B, right? That's 1 match. A,
you would do one of them, and then the other 3 you would just arrange any other way, and then multiply that whole thing by 4, right?
Yes, I see what you're saying. That's the best way to do it. Okay, so we start off with 4 factorial ways of arranging A, B, C, D, and we subtract the ways that where one of them is the same, but or at least one of them is the same. That means, okay, let's take A to be the same, and then that means that there's 3 factorial ways of arranging this one, right? Yes.
Yeah.
Wait, but that won't work, will it?
Well, I mean, I'm thinking in any case, no matter how those are arranged, right?
Mm-hmm.
The A is definitely going to be the same, so she's definitely going to lose this match. Now, depending on how it's arranged, she could have gotten all 4 cards the same, or 3 cards the same, or 2 cards the same, right? Depending on how the other 3 are arranged. So I guess that kind of does every possibility. If you multiply that whole thing by 4,
that's what I'm saying. That's why it wouldn't work. Because there are possibilities. For example, If she did B, C, D, A, that's no matches. So she does win sometimes, right?
Oh.
That's the problem.
Well,
okay.
I was thinking like the way we were like the A was gonna when I was saying multiply it by 4, I was saying like I meant like in term of you repeat the same process on every other letter, right? So like C is in the correct place, and then the other 3 letters around it, you could combine them 3 different ways.
Here's the thing though. There's CDB, there's 3 factorial ways of arranging that. Correct?
Mm-hmm.
And then if you multiply that by 4, you're going to get 4 factorial. So something's wrong with this approach. Because there's 4 factorial ways to arrange all of them to begin with.
Oh, I see what you mean.
Yeah. So what I would do is, well, one way to do is just to systematically list out the ways that she does win. Well, there's only a few ways that there's no matches. One way to have no matches is B, C, D, A. We can kind of work backwards here. I don't know if they'd allow that on the exam, but I know that there's 24 total ways of winning. So that means 8 times 3 is 24, 3 times 3 is 9. That means I have to find 9 ways that she can win. And if I can show all 9 ways that she can win and do that systematically, then that would work. So I can kind of work backwards, and that's kind of cheating, but I don't think if you don't let them find out, then it's a valid method, right?
That's true. But if she were to ask how many ways does she win, or like what's the probability of her winning a game, then I'd be not in good shape.
Well, it is asking how many ways does she win the game.
Yeah, but I'm saying it's probable that on this kind of question that they would also very well ask, like, what's the probability that she wins 3 out of 8 games?
Oh, that's.
Or what's the probability that what's the probability of her winning a game?
Then you wouldn't know. Okay, so let's take the other approach then. Let's go back. That's okay. I'm gonna go back to that approach where we say, okay, let's first take the case where 3 are the same. In that case, A, B, C are the same. That's one way. Another way where all 3 are all 3 are the same are. Oh wait, there's only one way that 3 can be the same or 4 can be the same. Right?
Oh, I see what you mean.
Because yeah, as soon as 3 are the same, 4 are the same. So there's only one way that 3 are the same. Now let's consider the way that 2 are the same. Okay, AB could be the same, and then this would have to be DC. BC could be the same. This could be DA, and then CD could be the same, and this would have to be BA. Right? There's 3 ways of doing that. Now we have to think about the ways where only one is the same. Well, it could be A, then CDB, or it could be A, and then DBC, right?
Yeah.
And then we would take B to be the same, and then we would take C to be the same, and then we would take D to be the same. And we can see that there's 2 times 4 ways, which is 8 ways, right? And I can list all these out. I would probably list these all out to get full credit, but just for the sake of, I think we understand what we're doing here, right? We would take B to be the same, and then you would say, okay, well, that has to be C or D, and then do the other possibilities. So 8 plus 3 plus 1 way. So 8 plus 3 is 11, plus 1 is 12. So there's 12 ways that she doesn't win the game. So if there's 4 factorial, which is 24, did we do something wrong? 24 minus 8 plus 3 is 11, plus 1 is 12. That's 12 ways. Oh my, we must have done something wrong. What are we doing wrong? A, C, D, B, A, D, B, C. Then B's would be the same, and C's would be the same than D's. 1, 2, 3, 4, 5, 6, 7, 8. 8 ways, 3 ways, 1 way. 9 plus 3, 12. I have to see the mark scheme because I don't know what's going on here. Okay. Oh, wait. So there's think we're doing method 2 here, right?
Yeah.
So Selena card A can match with Chloe card A, giving 6 possibilities for this happening. Why are there 15 ways? Oh my gosh. Always. These questions always get me. You know, sometimes on a good day, my mind just works. On other days, I have no idea how to do these types of problems. Okay.
I'm looking at method 1 because it's really intriguing me how like simplistic it looks.
This is from 2017 November. No, because I remember doing this problem.
It's the last problem, 2017.
I remember. Okay. There's 8 ways of 1 match, 6 ways of 2 matches. That's where we messed up. I see. When you're doing 2 matches, it's A, B, D, C. And then BC could match, CD could match, but then we forgot where AC matches. We forgot where AD matches. Yeah. Here. Okay. Going back to the ways that 2 can match, you could have A and B match, but not C and D. You could have A and C match, but not B and D. You could have A and D match. You could have B and C match. You could have B and D match. Then you could have C and D match. So that's 1, 2, 3, 4, 5, 6 ways. So instead of 3, that would have been a 6. So 8 plus 6 is 14 plus 1 is 15. So 4 factorial minus 15 is 24 minus 15, right? Which is 9. So now if you do 9 out of 24, that is equal to 3 out of 8. And that's how you get the answer.
Can you go to method 1 really quickly? I just
sure.
what they did for that.
It looks more simplistic, right?
Yeah.
What did they do? Okay. 4 factorial is 24. Mm-hmm. I think this is kind of what you were trying to do initially, and which was a good instinct. So A, B, C, D. So first they start with 4 factorial like we did. Consider ways of achieving no matches. So Chloe winning, no matches. Selena could deal B, C, or D as her first match for the possibilities of no matches, right?
Oh, yeah.
Okay.
Let's do 2 possibilities.
3 possible combinations for the remaining 3 cards. So you could have A, D, C. You could have D, A, C. Or you could have C, A, D. Like that, CDA. So now you'd work that out for the 3. Kind of a similar, it's like the opposite of what we did. So instead of working maximum subtract, instead you start with 0 and you build up. This is a building up approach. And then you do the same thing for the other one. So you'll have 3 times 3, which is 9 out of 24. Awesome. Yeah, you know, today's not the best day, as you can see. Part of it is we're exhausted at the end of the day. Sometimes that's another reason. I know I've noticed that when I do these at, you know, after ample amount of sleep and I do this with like a good sense of mind, it usually goes better. I'm not trying to make an excuse. Obviously, I can't do these right now. And that's concerning. It is concerning. But
I don't want to take the test at 3 p.m. tomorrow. That seems like the worst 2 hours of my life.
Afternoon seems pretty bad. Okay. This is. Let's try this one, and then we'll move on to because I think that this is a problem we haven't done, like these types of problems with points on a on a circumference. So number of distinct points are marked on the circumference of a circle, forming a polygon. Okay. Diagonals are drawn by joining all pairs of non-adjacent points. So let's say I have 4, right? Or actually, show on a diagram all diagonals if there are 5 points. Okay. 1, 2, 3, 4, 5. Okay. So I could have 1, 2, 3, right? I could have. Wait, those two are wait. Sorry, these two are adjacent, right? Yeah. So this can't join with this or that because they have to be adjacent.
Oh yeah.
So 1, 2. I could do 1, 2, and I could do that one there. That's it, right? I don't think there's any more. 1, 2, 3, 4. Yeah, I think that's only 2 ways, right?
I think so.
5 ways, and that would work with the next because it says show that the number of diagonals is n times n minus 3 over 2 if there are n points. What? So you have to show that there's that many diagonals. How would you do this? Okay, well, if there's 4 points, right, you have 2 ways. If you have 5 points, there are 5 ways. If you have 6 points, you can do 1, 2. And I think this has to do with combinations. Is this like a handshake problem? It feels like that. It feels like it's like a handshake problem.
It does, especially with the n times n minus 3 over 2.
Yeah.
It makes you think that it's like that.
There's n points, n choose. Would it be n choose n minus 2? You want to just try that real quick and see if that works? Because it's n, and then you're choosing n minus 2. That's kind of what it feels like to me. How many ways can you choose n minus 2 things out of n things?
Oh, I see what you're saying.
That's my logic. I'm not sure if that'll work, but let's try it. N factorial on n minus 2 factorial times n minus 2 factorial. So that would be 2 factorial, right?
Mm-hmm.
So we would get n times n minus 1 times n minus 2 factorial on n minus 2 factorial times 2. So I got n times n minus 1 on the top. They're getting n times n minus 3 on the top.
Then maybe, so you're saying that there's, of the amount of points, there's n minus 2 ways to arrange them so they're not on the diagonal.
Yeah, because if there's, what I'm saying is if there's 5 points, right? Let's say there's 5 points. Sorry, let me draw these better. Like they would look like in a circle. Yes. So say that there's 5 points. How many ways can I choose n minus 2? Because if there's 5, or is it simply just n choose 2? No, that wouldn't make sense. N choose 2 things, or maybe it's n choose 2. Maybe it's something where you're out of the n things, you're choosing 2 things, right? Because a diagonal has to be 2, right? You're choosing 2 out of n. And then you have to subtract the ways that you can form that, you can form the edges. Yeah, maybe this is the right way. N choose 2 minus how many ways can you do edges? Well, in a square you have 4 edges. So if you have 4 points, you have 4 edges, right? If you have a pentagon, you have 5 edges. If you have a hexagon, you have 6 edges, so minus n. Let me try this. Maybe this would be n factorial over n minus 2 factorial times 2 factorial minus n. Then this would be n times n minus 1 over 2 minus n over 2, 2n over 2. Does that seem right? 2n over 2. Yeah. Then we would get n squared minus n minus 2n on 2. That would be n squared minus 3n on 2, which would be n times n minus 3 on 2. Yeah, this is the way to do it. Does that make sense what we did, Maham? Or no?
I'm genuinely like...
Yeah, okay, sure. Let me just read. Okay, now that I figured it out.
I get it, like, just the way you set it up. Just I'm trying to explain how you set it up.
Sure. Of course. So let's, if we go back to the issue is the first thing, without even worrying about restrictions, how many ways, if I have n points, how many ways can I join any 2 points on here? It's n choose 2, right? Mm-hmm. But the problem is this is a polygon, and I'm only concerned about the diagonals of the polygon. So if I have 5 points here, the edges don't count, because that's why they're saying diagonals are drawn by joining non-adjacent points. Because if they're adjacent points, they become edges of the polygon, not the diagonals. So how many edges does a polygon have? Well, a polygon has n edges. So you have to subtract n from the n choose 2. So if you do n choose 2 minus n, and you set up the factorial, it'll work out to be n times n minus 3 over 2.
Oh, I see, because one line to that point, one line to that point, and then like each line to each point, that's your n, and that would give you an edge.
Yeah.
And then n is your total number of points, and you're choosing 2. Okay. So
once again, see, I don't know how to approach these. It's just kind of, you just have to take a wild guess and keep poking at it until it comes out. Honestly, that's what it feels like sometimes. How did they do it? I'm curious to see what they did. Correct argument for each point joins to n minus 3 other points. Okay, well, that's not what they did. They did something similar, but not that.
Each point is joined to n minus 3 other points.
Yeah, okay, so they essentially kind of did the n choose n minus 3, I think. They kind of took the initial approach that we did, except our initial approach was wrong because we did n choose n minus 2 instead of n minus 3. If you do n minus 3, will that work? Because logically that makes sense, right? It's n choosing n minus 3, because the 3 points already make edges. So n choose n minus 3 would be n factorial on n minus 3 factorial times 3 factorial, which would be what? N times n minus 1 times n minus 2 on 3 times 2. That doesn't seem right, but I'm going to keep going in case it works out. No, that's not going to work out. That's not right. Then maybe they did something wrong. Or not, didn't do something wrong. I'm sorry. We're doing something wrong with this, with interpreting their method. What are they doing here? Each point joins to n minus 3 other points. You know what? Our method works, actually. It's logical. It works. We would get it.
I don't get where they're getting the n minus 3 from, because like your point makes more sense, right? Because you're saying that it minus n, like it joining to any of the edge points.
Sure.
I don't get where the minus 3 is coming in, you know?
Sure.
Because if you're joining it, right? Only 2 points would give you a diagonal if you think about it in that way. If you're joining n to any other points, 2 points.
They're saying, okay, so if I have n points, maybe it's n p n minus 3. But order doesn't matter. That doesn't make sense. It's joining to n minus 3 points. Okay. You know what, Maham? I think our method makes sense, and I'm happy with that. Do you want to take more time figuring this out, or I'm fine with it.
We can go next. It's fine.
Yeah. Sometimes it's hopeless. Sometimes.
Yeah.
Let's actually finish this problem because I feel like this would be a good problem just in general to practice for this unit. Given that there are more than 1 million diagonals, determine the least number of points for which this is possible. Well, how would you do that? If we know that n times n minus 3 over 2 is the number of diagonals, and we're saying that there's more than 1 million diagonals, then this is simply greater than 1 million, right? And determine the least number of points for which this is true. So you can just test out different values of n, or you can plug this into your calculator and check the inequality and see the first value for which n is greater than 1 million. What I would do is I would write this as n squared minus 3n over 2 minus 1 million. Did I forget a 0 here? Yeah, I forgot a 0. 1, 0, 0, 0, 0, 0, and that's greater than 0. I would plug that into my calculator and see for what n that holds true. And then that's your answer. I'm sure that's
okay.
How else you would do that. Yeah, that's attempting to solve that inequality, exactly. Okay, now, nice problems. These I like. The random variable x follows p and p has mean 4 and variance 3. Determine n and determine p. Well, we know that mean 4 equals np. We know that variance 3 equals np times 1 minus p. So np we can substitute in. 3 equals 4 times 1 minus p. That means 1 minus p equals 3/4, which is equal to 0.75. So that means p equals 0.25, which is 1/4. And then if p is 1/4, then that means n has to be 16, right?
Yeah.
4 times 3/4. Okay, easy. See, these are algebra. Algebra problems we can all do, right? 16 1/4, good. Okay.
So before we do the second part of it, I want to ask this really quick question.
Of course.
So whenever we're doing a discrete random variable and you're finding a probability, you're going to like if you're like writing it out, right? Like the probability of this, you would you like if you're saying the probability of something, you would not include the like, oh man, how do I even phrase this? Because for one of them, it's like you have to like continuous. It's any group, and so like,
I see what you're saying.
Do you get what I'm saying? Like the
cumulative. Are you talking about cumulative?
Huh?
Like probability of x is less than. Like, are you talking about
cumulative? So I'm wondering like when you would say like less than or equal to or just less than.
I see. Okay, so say that it says what is the probability. If it ever asks simply in the question, what's the probability that the outcome is greater than x equals 3? It has to be greater than. If they specify greater than, probability of x is greater than 3 in a binomial, in a discrete distribution, is probability of x is greater than or equal to 4, because it can't touch 3. So it's greater than or equal.
Got it. Okay. I see what you're saying. But if you're doing a continuous variable and you're doing x
then it's just
it's this like in the calculator it's this you just plug it in as is.
Because probability of x greater than 3 is the same as probability of x is greater than or equal to 3.
Okay.
Right.
But if you're putting binomial in the calculator and it's saying something is less than or greater than but not equal to, you have to sort of change. So like if it was less than 3, you'd have to do x is greater than equal to 2 when you're putting in a calculator.
So in this case, you would do 1 minus probability of x is less than or equal to 3. So we're actually going back to 3 because our calculator, we have to put in binom CDF NP3, not 4 here, because we're concerned about everything. If this is 3, we're concerned about everything greater than 3 and not including 3. So when we are doing the binomial, when we're doing the cumulative, the CDF, we have to include 3 in that. So that's why we have to include. And always our CDF is always less than or equal to. So we always include 3. So sometimes it's easier to think of it visually. I would draw it out sometimes. I think drawing it out would help. Like do a little quick mental picture. Okay, maybe you don't need to physically draw it out, but some sort of mental picture to understand. Okay, greater than 3 means it's 1 minus less than or equal to 3.
Binomial CDF is always solving for x is less than or equal to something, right? I think you just said that, but
always, yeah. On a calculator, binomial CDF always is less than or equal to whatever.
So if it's like I mean, this one is like 1 or 3, right? This is a little different, but I'm saying like if it was asking for like let's say like the probability that x is greater than or so greater than, like, let's say 4,
okay,
right? Then you would do 1 minus x is less than 3, or less than or equal to 3.
Less than or equal to 4. Remember, think about it. X is greater than 4. X is greater than 4. That means I'm not including 4. So when I do the binomial CDF, I have to include 4 because I'm looking for the complement. Once again, draw that picture. So this right here, if this is 4 right here, I would draw a dashed line to represent greater than, and this is 4. When I'm doing the complement of whatever's in here, I have to include 4 because I didn't include it previously. So I have to probability x is less than or equal to 4.
Oh, I see what you're saying.
Right?
Okay, I get it.
Okay.
I get it.
Yeah, the discrete nature of the variable often just sometimes the continuous is easier because it's just calculus. You just plug in the numbers and you can easily do those. These are discrete makes you think a little bit more. Okay, so this is probability x is equal to 1 or probability of x is equal to 3. You would just plug it in your calculator binomial PDF. Obviously don't write it out on the paper binomial PDF, but binomial PDF. N, which was 16, I believe. P was 1/4. What was it? I can't remember. I think it was 16 and 1/4. So we would plug in binomial PDF parentheses 16, 1/4, 1 plus binomial PDF 16, 1/4, 3. And that should give you the answer. Yeah. And this is if this were paper 1, you would have to work it out this way with the but that's just the definition of binomial distribution. Okay, good. This is from 2014. We actually did this one, right? We did this one. I remember doing something like this with a pack of 9 cards.
Yeah. We've done this one before.
Okay, all right. Do you want to go to Oxford now?
Sure.
If you're running out of time, let me know. I don't want to hold you back just because we're doing problems.
No, I'm gonna be studying this anyway, so
makes sense. No, I completely understand. Okay. Topic. Oh, so that's descriptive stats. I feel like descriptive stats is we actually did the 2 IB problems from descriptive stats on that thing. Do they have probability in here? This one. I think it's this one, right?
Modeling
page 16. It's this unit. Because I remember when the problems that she gave us for descriptive stats. If I go back to that, stats and prob, descriptive stats. The problems that she gave us for the descriptive stats were actually from the Oxford book, as far as I can remember. Let me just open it up real quick just to confirm. Yeah, these are from the Oxford book, like directly from the Oxford book, paper 2 problems that we did. Okay, so that was from unit 5. So we've done unit 5. We could go back to page 51 here and just review the counting principles, but we just did that on straight from IB problems, so I'm not going to do that if that's okay with you. I think we can go straight to topic or chapter 11 in the book because that's kind of the distributions, probability, and that kind of thing. Let's go to 727. 727. Come on, okay. There we go. Okay. Let's see if they have a chapter review that we can do real quick. Okay. No, that's exercise. That's a chapter summary. Let's just look through the chapter summary real quick. We know most of this stuff, but just to make sure we've covered everything. Probability, simple, axiom, yeah. Actually, do you want to go through this stuff or no? Looks like we know this stuff.
I'm pretty good with it. Okay. If you want to do it, but I don't think it's something that sure. It's not the hardest thing,
Yeah, the definitions I think we understand. It's the doing the problems. Yeah. That's Okay. Let's look at some of the IB style problems, exam style questions. These are good questions to look at. Okay. Where do you want to start? Do we just want to go through all of them, or how do you want to do this?
I have to. I
understand.
I go downstairs for dinner in a little bit, so it's like, we can find something that just seems kind of like challenging or more. Honestly, I'm not super great with table questions.
Do you want to try this one?
Sure. Wait, actually, let me. I want to see what something that's like. What's that other one? The one with the percents on it. The table. Go up a little bit.
Oh, this one here?
Yeah.
Okay, so this is an exam style. This isn't an exam style question, but we can definitely do it. There's no reason not to. Okay. Let's take a look. Okay. In factory, chocolate bars are produced on, oh my gosh, sorry. Chocolate bars give me trauma now because all I can think of chocolate bars is that one problem from IB where, remember that one we went over in class where like, the
yes, yeah, I know.
That problem is traumatic to me at this point because so much. Okay.
Her trying to explain it to you was really funny too, because it like took everything out of her. You could tell, like it was, yeah. It was just like an all around.
It's just a draining problem. It just sucks everything out of you. Okay. A, B, C, or D. Small percentage of bars are not produced for sale. Okay. So percentage of faulty chocolate bars and percentage of total outcome. Okay. So of the faulty bars, A produces 1%, and then A produces 35% of all the bars altogether. Does that make sense?
Yeah.
Okay. Find the probability that a bar chosen at random from the whole output is faulty. So probability of faulty. Okay. So this here is actually the probability of A given faulty, right?
Mm-hmm.
Because it's taking the faulty as a sample space. Okay. So how can we figure out the probability of faulty? We would have to add up probability of A given faulty, probability of B given faulty, C given faulty, and D given faulty, right?
Yeah.
Because that's exhaustive. That covers all the possibilities of faulty. So if we just add this plus this plus this plus this, what are we going to get? 4, 6, 8.5%, right?
Yeah.
So this is 0.085. That's the probability of being faulty. We'll check our answers in a bit, but let's just finish this problem and then we'll go down and check. Find the probability that the faulty bar comes from conveyor belt D. Okay, so probability. Go ahead.
So so it's saying that given that it's faulty, find that it comes from D.
Yes.
Okay.
So this would be.
Oh.
Wait. The wording in these problems are weird. The Oxford book is a bit weird on that. I've seen their wording is very weird. Because is this asking for faulty given D or D given faulty?
That a faulty bar comes from the conveyor belt D. I think that it's given that it's faulty, but does it come from, like, what's the probability that it comes from conveyor belt D? So our sample space is that, like, of the faulty.
But then that would be too easy, I think.
But then that would be too easy.
Then I think this is asking for faulty given D.
No, but that sucks. It's like I would have never thought of it like that, you know?
Yeah, it's a wording problem. So it comes from conveyor belt D. So it's out of the ones from D. What's the probability that it's faulty? So what's faulty given that it comes from D? That's how I would think of it.
Oh.
So then this has to be probability of D intersection faulty over probability of D. Okay, well, probability of D is 21 out of the sum of all of these. So that's 21 divided by 5 plus 4 is 9.
Well, it's saying that it's a percentage of the total outcome.
Oh, I'm sorry, that's percentage. So, you're right. Sorry, I read that wrong. Yeah. 0.21.
But they didn't put the percent there for some reason. Yeah, I don't know why.
Yeah. that would have thrown me off. See, that's what throws me off. It's these small details. Okay. So 0.21 is a probability of D. Now, how do we figure out probability of D intersection faulty?
So D and faulty.
Yeah.
So
I think we have to go back to this here. Here we know that this is probability of D given faulty, right?
yes.
Does that make sense, Maham? Like it's out of the ones that are faulty, this is D. So by the formula, we know that probability of D given faulty is equal to probability of D intersection faulty over probability of faulty. And we solved probability of faulty was 0.085. So that means we know that probability of D intersection faulty equals probability of D given faulty times probability of faulty. D given faulty is 0.02. Faulty on its own is 0.085. So if this is probability of D intersection faulty. So if we put that in here, 0.02 times 0.085, and we plug that into our calculator, what do we get? 0.02 times 0.085 all over 0.21. We get approximately 0.00810. I think they want 2 sig figs, right? Just 8-1.
Okay. So you're saying that, okay, I kind of see what you did, but I'm just trying to like conceptualize it. So it's 0.02, which is the percentage of faulty the faulty bars that come from D, and you're saying that it's the probability of D and well I think of when you say intersection you mean D and faulty, right?
Yeah.
Okay, so D and faulty. So I'm kind of confused on why it's not just 0.2 because
why it's not just 0.02?
0.02, yeah.
Because this is percentage of faulty chocolate bars. So this is what this is saying is out of the sample space here is the faulty. So if this is faulty, the probability that it comes from D is 0.02. Okay? That's different from saying from all of the bars that are out there, good and bad, what is the probability that I'm getting a faulty bar from D?
Oh, I see what you're saying. Okay.
Because here's the thing. This is D given faulty.
Mm-hmm.
And then I use the formula to figure out what the intersection faulty is.
I see.
It's just like a tree diagram. If you have A prime, and then you have B prime, B prime, the probability of A intersection B prime isn't the same as whatever is here. Because whatever is there is the probability of B given A prime. This is the probability that B happens after A happens.
Got it. Okay.
Right? So this is an A intersection B prime. You would have to multiply this, because that would be B given A times probability of A. We're doing the same thing here. You can think of this as a tree diagram. You can think of fault. You can actually do either first. You can do A, B, C, D, faulty, not faulty, or I'll just say good for faulty, good, faulty, good, faulty, good. They tell you that out of the total, A is 0.35, B is that, C is that, D is that, and then out of the, oh my, okay, actually this wouldn't work the way I've set it up to match with the data. To match with the data, you would have to do faulty, not faulty, A, B, C, D, A, B, C, D. And they only give you that this is 0.01, this is 0.03, and so on and so forth. They're giving the value of A out of the ones that are faulty, not the same as this value of faulty and value of D given faulty. Does that help to visualize it that way?
Yeah. I think just the way I was thinking about it was off, but yeah,
okay,
that makes sense.
Okay.
Okay.
Let's go down to the. Hold on. How can I go down to the answers without having to keep scrolling back? Okay, let's remember the page number. This is page 740. I'm going to go down to the solutions. Sorry, do you remember what number that was?
10.
10,
the monster.
Where are we? Oh, yes, that's the monster. Okay. 10, 10, 10. 0.0. Hold on. What? 0.0197 and 0.213. That's not right. What we did then. Maybe I understood the problem wrong.
0.0197 and 0.213. Okay.
How did they get 0.0197?
Is that what we got for the first one? No, right?
No, we got 0.085 because we just added these percentages together.
Oh, yeah. All right. So ball chosen at random from the whole output is faulty. Okay.
Hold on. Let me see if I can find the work solutions for the Oxford book. I actually don't think they've released them. Yeah, I don't think I have the solutions for those, the work solutions.
It's saying from the whole outcome, and then the percentage of the total outcome. So
I'm confused. Maybe I misinterpreted this. Maybe you interpreted correctly. Maybe is this saying probability of faulty given A?
saying the probability of the whole output is faulty.
Maybe this is saying what's the probability of faulty out of the ones from A.
Yeah, it's saying the whole output. So you take the whole output, and then from that you find faulty.
So from A, the ones that are faulty. See, this is a problem with these types of
from the whole output. So the total outcome.
Oh, you're saying that this is from the total outcome of like every single bar.
You're asking for A, right?
Yeah, this 1% here.
So it's saying find the probability that a bar chosen at random from the whole output is faulty. So if the total amount, and that's the percentage of faulty chocolate bars. So there's 8.5% total faulty.
Hold on. Let me see if I can find the work solutions for this, because there has to be. I think I'm just understanding. I'm not understanding it properly. Oxford analysis and approaches work solutions. On the Reddit page, work solutions, HL. Oh, maybe. Hold on. I'll have to download it. Do you want to move on to a different problem and come back to this one while the solutions download?
Yeah, sure.
Okay. Sorry about that. I really don't have any idea on what this problem is.
No, it's fine. It's like it's like seemingly easy, but then it's not at all.
The problem is the wording half the time. I mean, sometimes I just don't understand what's going on in the problem itself. You know what I mean?
Mm-hmm.
Okay. Well, oh, actually, just finished downloading. Let me see. Let's see if it loads. Okay. Work solutions. This is for. Oh, Well, now it's gonna lie. It's gonna be for which one? Oh, okay. Number 10 on median, blah blah blah. Okay, it's still the exercise. Chapter review. Okay. Okay. Probability of faulty is that times that plus that.
I was literally doing that on my calculator just now. I was multiplying 0.01 times 0.35. I was just doing that, but for some reason I think I was doing it too fast and I got a different number. Yeah,
so,
I was literally just
doing
it. I
think we all agree that this is probability of A, this is probability of B, this is probability of C, this is probability of D. This is the probability of faulty given A, right?
Yes.
Yeah.
So it's kind of asking for the expected value.
It's not expected. No, it wouldn't be expected. It's asking for what it's asking. It's probably that it's faulty. It's because here's the thing: probability of faulty given A. It's like a tree diagram here. It's like saying A, B, C, D, and then it's saying faulty, not faulty, faulty, not faulty, faulty, not faulty, faulty, not faulty. And the values it gives you here are the 0.35, 0.2, and so on and so forth. And the values it gives you here is 0.01, 0.03, 0.025. So now you say, okay, to get all the faulties, you do this times this, plus this times this. You multiply all the pathways. See, that, oh my gosh. I just didn't understand what this was asking for. Because honestly, though, I thought that this was saying this is the probability of A given faulty.
Yeah, I see what you mean. And now with this tree diagram, B makes perfect sense too.
Yeah, and now the probability that it comes from conveyor belt, that a faulty bar comes from conveyor belt D, is probability of, and now it's what you were asking, D given faulty, not what I was. See, and that's the thing. Once again, it's wording. How do I know whether it's D given faulty or faulty given D? I think on the exam, it's more clear. I think the Oxford book makes it complicated when it comes to the wording on these types of problems. But that would be D intersection faulty on probability of faulty. So it would be 0.02
see, this is like so
divided by this number, which I think is the right answer. Let's go back to the work solutions and check.
Oh, let's.
That's the question bank. 0.02 times. Oh, sorry. Yeah, I forgot to multiply. Yeah, 0.02 times 0.21 over the faulty, which is the 0.197. 0.197. That was a bad problem.
Yeah, it's 0.21.
Yeah, 0.0213 exactly. In my opinion, I might be making an excuse, but I honestly think that question was badly worded.
I agree. I didn't.
How else are you supposed to know which one's what? Yeah. Okay.
Yeah, exactly.
Are you comfortable with normal distributions? I think we're good with. I think the continuous ones are fine, right? The continuous ones you're comfortable with.
Honestly, yeah, I'm fine with. Yeah, I've been doing them for like a really, really long time. I've gotten like really, really like good with z-score, normal distribution, and all of that.
Those are those are more like, and those are more calculation stuff. Calculation stuff isn't that hard. It's the conceptual stuff that's actually kind of hard.
Yeah.
Okay. Let's do.
But yeah, if we can do one more.
Sure. Can we do two more? Can we do 12 and then can we do 14? You have time?
Yeah, sure.
Okay. All right. Let's do 12 and 14.
Yeah.
Two events A and B are independent. It's given that A equals 0.3 and B equals 0.8. State with the reason whether events A and B are mutually exclusive. What would be the answer?
If they're independent, they're not mutually exclusive, are they?
Yeah. So actually, by definition, mutually exclusive events have to be dependent. Because
exactly.
Right. Because if it's an A, given that it's an A, we know for sure it can't be an B. So that shows that it's not independent. That shows, So because, but I don't know if they'd allow that. If you want to show it mathematically, I guess what you could do is you could say probability of A intersection B, because they're independent, is 0.24.
Probability of A times probability of B.
And then probability of A union B, if it were mutually exclusive, would just be 1.1. But since it's not mutually exclusive, that's how to do it. Probability of A intersection B does not equal 0. In order for it to be mutually exclusive, probability of A intersection B has to be 0.
Oh, yeah.
That's how I would show that. So I think that suffices. Let's go to the work solution and see what they're saying for that.
Oh yeah, mutually exclusive. I don't know why I was saying mutually exclusive is like it could be one or the other, but mutually exclusive means it can only be one or the other.
Yeah, that's what they're saying. Exactly what we just said. Okay, good. Find the probability of each of the following events. Well, A intersection we just found is 0.24, right?
Mm-hmm.
What would A union B be?
That'd be A or probability of A plus probability of B minus probability of A union B.
Intersection B, right?
Or intersection B. Yeah.
I know what you meant. Okay.
I just say and or. I don't.
And then so now we subtract that from that. Whatever we get, 10 minus 4 is 6. 10 minus 4 is 6 is 1, 0. 10 minus 2 is 8. So 0.86. I believe so. And then A given B prime would be A and B prime over B prime, right?
Yeah.
B prime we know has to be 0.2. What about A and B prime?
A and B prime. Oh man, I'd like normally draw these out.
Can I? Yeah. When I do these, I don't actually use the formulas. I do the kind of. Do you remember what the Heath book does with like the A, B, C, D?
Yeah, that's exactly what I do.
I'd rather be able to see this and then do algebra and then say, okay, that's A, that's B. Let's call this A.
A and B is what again?
Sorry?
A and B is what again? What'd we say? 0.8? Okay.
Yeah.
Okay.
0.86 for A union B.
Oh, okay.
Oh, wait, Maham, this would be A or B. A union B would be A or B, not A.
Oh, yeah. I don't know why I keep saying that.
It's confusing because colloquially when we say, say that, we kind of just say and is, everything, but that's not always the case in math. Okay. So we know that A plus B plus C is A union B equals 0.86, which we found out. We know that B equals 0.24 because they're independent. We know that A equals what? 0.3, and we know that C equals 0.8, according to the diagram I just drew. A intersection B prime would be A and D, right? Mm-hmm. No, just A.
A intersection B prime?
Sorry, I wrote this out wrong. A plus B equals 0.3, and then
yeah, that's what I was a little confused at what you were trying to say. I thought something like capital A and capital B.
Yeah. So A plus B equals 0.3, B plus C equals 0.8. And then we were trying to find A intersection B prime. A intersection B prime would be just little a, right? Mm-hmm. Little a, how can we find just what little a is?
You would do what is it? So 0.3 is all of A, and then your B value is A and B.
Yeah, so A plus B, small a plus small b equals 0.3. Mm-hmm. And because we know what small b is from A intersection B, we know that A equals 0.3 minus 0.24, which is equal to 0.06, right?
Yeah.
So it would be 0.06 divided by 0.02, which happens to be 6 over 20, which would be 2 times 3, 2 times 10, so 0.3 would be the answer to this one. And then what about A prime intersection B? A not in A, but in B is just C, right?
Yeah.
So little c would be 0.8 minus 0.24, which is what?
0.56, I think.
0.56, exactly. Okay, now let's check. Hopefully it's all right. Okay. 0.24 for A intersection B. 0.86 for part 2. For part 3, it's 0.3 as we got, and then yeah, exactly. Perfect. Okay. One more problem and we'll call it a day. It's been quite a long time and I don't want to hold you any longer.
Okay. I mean, again, I just be studying. I'm gonna break for dinner after this, but then I'm gonna start studying again.
Okay. This is normal distribution. Let's not worry about that because we can do continuous. Let's do this one because this looks like a binomial one, right?
14?
14. Looks like binomial to me.
Okay.
Or do you want to do 13? Which one do you want to do? Your choice.
14's fine. We can do 14.
All right. Approximately 4% of eggs are cracked, and Jerry buys 24 eggs. Okay. What are the if 4% of eggs are cracked, we can say that the x follows a binomial distribution with n is 24, right? 24 trials. Probability, the p-value is 0.04, right? Okay, yes. So what's the probability that exactly 2 are cracked? That would just be probability of x equals 2. Plug that into your calculator. Binom PDF. Okay. So PDF of 24, 24, 0.04, 2. We get approximately 0.180. Let me know if that's what you get.
Yeah, that's what I got too.
Perfect. Okay.
No more than can I try the B one?
Of course, always.
So find the probability that Jerry buys no more than 4 cracked eggs. So that means P is X is less than 4. Yes.
No more than 4.
P probability of X is less than 4.
Is it less than or equal to 4?
Oh, no more than 4. Yeah, sorry. So
no, I'm trying to think. I'm not implying that it is. You might be right that it's just X is less than 4.
No more than 4. Yeah, because that's at most 4.
At most 4. So he can buy 4, right?
Yeah, I assume that he can buy 4.
So yeah. You're fine. Keep going.
So then, and because it has to be less than or equal to 4, we can just do binomial CDF just with our n, p, and x value.
Exactly. Binom CDF 24 0.04, comma 4 0.998.
I didn't put it in, but I'm sure it's gonna come out this. Find the probability that Jerry buys at least 2 cracked eggs. Okay, so the probability of that x is greater than or equal to 2. All right. So that's 1 minus the probability that x is less than 2.
That is correct, but your binomial CDF function doesn't.
But binomial CDF only functions in that. So then that would mean it has to be 1 minus p is x is less than or equal to 1.
Exactly. Good. All right. So now let's just plug that in. 1 minus binomial CDF of 24, 0.04, 1, and we get approximately 0.249. And then finally, find the variance.
The variance of I haven't memorized these, so I just
what's the variance is just NP NPQ. That's the variance. So it would be N is 24 times 0.04 times 0.96. Right?
Yes.
Okay. So we have 24 times 0.04 times 0.96. And we get that the variance is approximately 0.9. Actually, we can just say it equals. It equals 0.9216. Okay? All right, let's check. 14, and this was paper 2, so we were allowed calculator. Okay. 0.180, perfect. 0.998, good. 0.249, good. 0.922, good is the variance. We said it was 9216, which is fine. We gave the exact answer. This is actually wrong because they said it's equal to 9 point. If you could say it's approximately equal to 0.922, but then you have to include the approximate sign. Otherwise, that's implying that it equals, and I don't think that that's right to say that. Mm-hmm. Okay. All right. If you work on this one later, since you were saying you were struggling with table problems, I would just work this out with algebra. Usually, these types of problems, you can just like set it up with the formulas, and you should be fine with those. Right?
Yeah, this is fine, right? Because it's just like if you're trying to find the mean, it's just your x value times your probability of x for that given x, right? And you would just multiply it summation.
Yeah, this is like the one we had on our quiz, right?
Yeah.
Okay. All right. Anything else you want to? Any last things before we end today?
I think I'm good for now. If I have questions, I might ask you later. But
I think the big thing for me, I don't want to speak for you, but I think the big thing for me, and it seems like for all of us, really, is the permutations and combinations stuff. Like,
for sure, it's just because no amount of studying is going to make you perfect in it.
Yeah,
it's just like not possible.
I think the best approach is just to take your time on this. I know when I get rushed, I want to finish the problem quickly because I get anxious, and then what happens is I miss, like what was happening with today. Like remember, we missed certain ones because we didn't think through all the different possibilities. Yeah. So if you just take your time and just think, okay, have I exhausted every possible option? So honestly, I would even save these questions probably for the end. I wouldn't spend too much time on them in the beginning.
Mm-hmm. Or like save like part C for the end. Like do part A and B and then leave part C for the end.
Okay, all right, I'm going to stop the recording.